Hello.
Hello.
Hi.
Yes, sir. I can hear you.
Okay. So we'll start our physics class. Uh, the thing is, in physics, what we'll have to first figure out is calculus. Okay. So calculus, which is a maths topic for 12th standard, but that is absolutely essential before we can do any physics. Okay. So what we will do is we'll start off from calculus. Don't mute yourself. Uh, Otherwise, it is very weird.
Yes.
Uh, so you have that Thomas and Finney book, yeah?
Yes. I need like 1 minute to get it. Just
Yeah,
one
yeah,
second.
get it. Thomas and Finney calculus.
Sir, I have the Cengage
Calculus.
calculus book. Is it that
But you
one?
don't have, no, no, you don't have this one, right? So I'll send you a PDF version of this. PDF of this. Okay. After the class, I'll send it to you.
Yes, sir.
So you don't need to buy the physical copy. You can just read from the PDF. Okay.
Yes, sir.
So the idea is that this is a nice theoretical introduction. Cengage book is for like JEE calculus. So this is a nice theoretical introduction. It explains every concept very well. So while we are learning physics and we are trying to do calculus right now only for the purposes of being able to do physics, right?
Yes, sir.
So later, anyway, we will be studying calculus in much more detail when we come to it in maths. But since we cannot progress further in physics without knowing calculus, that's why we are doing it right now. So right now, it's not about problem solving or difficult problems in calculus. So we will not be using the Cengage book. We'll be trying to understand the concepts here, right? And we should be able to basically know what all of this is about. So
Yes, sir.
today and maybe next week also, I'll be spending time on calculus itself. If you look at your HCV textbook, if you look at HCV, there is a chapter 2 called Physics and Mathematics, right? HCV volume 1, I think there is a chapter 2, Physics and Mathematics, right?
1 second.
Hmm.
Yes, sir. Physics and mathematics.
So physics and mathematics has some ideas like vectors. It has some ideas like vectors. Then it has calculus, where he talks about differential and integral calculus. So that is a very brief introduction. Differential calculus and integral calculus. Very briefly, he has mentioned it. What we will do is spend a little more time, 2 weeks or so, on it and make it understandable. Okay. So right now we are working on this physics and mathematics section. Okay. So you can refer to HCV whenever you feel like. And I will send you the PDF of this Thomas and Finney after the class. So you should read that. Okay.
Yes, sir.
So what this calculus idea is about. So for example, uh, if you want to find, if you want to find the area, the area of this graph. So I'll show you. Suppose suppose y is equal to x square is the graph, right? This is y is equal to x square because this is y axis, this is x axis. So 1 comma 1 1 1, let's say, and this is 2 comma 4, let's say, right? This point is 2 comma 4, right? So
Yes.
this is a rough graph of y is equal to x square. Now suppose somebody asks you this, find the area under this graph in this portion. Okay, area under the curve in this portion, this area, this shaded area. Okay, now how would you go about doing this, right? this is a this is really problematic, right?
Yes.
The problem is that it is not some nice standard figures that geometry, right? Circles, squares, rectangles, parallelograms, triangles, so on, right? But
Yes, sir.
this is a curve, right? It's like a curved thing, right?
So dividing into like very small figures of
Hmm.
like rectangles maybe.
So have you done this before? Has someone taught you this before?
Not in a lot of detail, but like briefly.
Where?
In Allen, I've done it.
In Allen they have done it. So right now, recently, or last year or something?
It was previously, but now they've started calculus. But I didn't attend the last few classes because I had school exams like 2 days back.
So they are starting to discuss calculus.
Yes.
So what have they discussed so far?
I think they've done differentiation and they've started integration.
Okay, great. So differentiation, then you know what it means, huh?
It's like the slope at a point, at a certain point.
Slope of the function at a certain point. Okay, that makes my job a little easier. Uh, at a point, and this area thing is integration. Okay,
Yes.
so this is a method how to find this area. This is a method by called integration. Okay, great. So you know a little bit of basics. So I will just, it will be easier for me. Uh, so first thing that we want to understand is what is a function. Okay, because when they are saying differentiate a function, what is a function? So have they told you that?
I didn't attend these classes, so there's like not a lot that I remember from earlier. So
So this was how
like
long ago?
1 year back.
This introductory to calculus was done 1 year back, huh?
Yes, sir.
Not in this January onwards.
It was also done here, but I didn't attend these ones.
Oh, okay. Okay. So what is a function? I mean, just whatever sense you have of it.
A
So someone
relation
says,
of X and Y.
someone says this, y is equal to fx. So it means a relation between x and y, right?
Yes.
Between x and y, and that relation could be specified in any way. You could have said y is equal to x squared, or y is equal to x, y is equal to sine x, right? Or you could do whatever, 1 by x squared, right? All of these are legitimate functions. Log of x,
Yes.
2 power x, all of these are different ways in which the y and x variables are related, right?
Yes, sir.
So now we will go into a slightly more detail about this. So what it actually means is that, think of a function, and you will see this description given in Thomas and Finney also. Think of a function as a machine. It's a machine, it gets some input x and it gives out some output y, right?
Yes, sir.
So this is the input, this is my machine, this is my function, right? And this is my output. Now, it is not necessary that you always understand how the machine works, okay? Just like a car, you don't really know all the time how it works, right?
Yes, sir.
Just hold on for a second. Yeah. So what I was saying was, sometimes the function could be quite mysterious, okay? Like you don't know what is going on, but some inputs you're giving and it is getting some outputs, right? Now, how would you classify, like what are the restrictions? Like what will you call a good machine or a workable machine, right? Workable machine. Like if you just think commonsensically, what are the restrictions that have to happen, or properties that a good machine has to have, right?
It needs to like give the desirable output.
Desirable output in the sense, don't think of the machine as serving some purpose. Right now it is a machine, okay, it does something, right? So
Yes, sir.
how will you say that the machine is fine or machine works, right?
If it's working, like if
if Exactly. Specify that. If it's working means what?
I mean, if it's able to use whichever input source it
Uh-huh.
has to perform
Correct.
whatever function it's supposed to.
So basically, if it should be, it should not be like I gave an input and it didn't give an output, right?
Yes.
So for every input that you give, right, there should be an output. The machine should not just hold, stop and do nothing, right? There should be an output, right? This is making sense.
Yes.
It should not be like you gave some input and nothing happened. Then you don't even know whether it's working or whether it's not working, what is going on, right? Right.
Yes.
The second thing is, uh, can any input be given to a machine?
No, it has to be like the specific input which the machine requires.
Correct. So, for example, I cannot give apples as input to a printer, right?
Yes.
That will not work. Apples should be given as input to a blender, right?
Yes.
So there is a set of allowable inputs, right? Good inputs or proper inputs for a particular machine, right?
Yes.
Puts for a particular machine. So depending on a different machine could have different set of inputs, right? Correct.
Yes.
So basically what we are saying is that any function has a set of good inputs or allowable inputs. You cannot just give any arbitrary number as input and expect a response, right?
Yes.
And a function should be such that whatever input you are giving finally, there should be some output as a result of it, right?
Yes, sir.
So now we will talk about these same ideas in terms of sets, and we'll classify these ideas properly. So let's say we have two sets, they have some elements, okay, and this is another set with some elements, okay. Now we say that a function is a relation between set A and set B, is a relation between basically elements of set A and elements of set B, right? Set A
Yes,
and
sir.
set B. So this, let's call this one the input set, okay? Input set. This is the input set, that is A, right? That is sometimes called, the term for that, technical term for that is domain. Okay. So if someone asks you what is the domain of a particular function, you have to give him the set of allowable inputs to that function, right?
Allowable inputs. Yes.
Allowable inputs. So like whatever inputs are good for that function, right? So for example, if my function was y is equal to root x, right? Correct.
Yes, sir.
I should not give -3 to it, right?
Yes, sir.
If I give -3 to it, doesn't make a lot of sense.
Mm.
It will
It
not
has
be
to be
able to
real,
take
right?
roots and all, right?
Yes, sir.
So similarly, if my function was y is equal to 1 by x minus 2, right? I should not give x is equal to 2 as an input to it.
Yes, sir.
Any other number is fine here, except x is equal to 2, right?
Yes.
Here, every number which is negative is not cool. So you have to send something which is positive or 0, right?
Yes.
So the set or the domain set for the first one will be all the non-negative numbers, right? And domain set for the second function will be all the numbers except 2, correct?
Yes. Yes.
Because all of those are allowable inputs, right? Correct.
Yes.
Now, one important restriction is that once you have decided your domain set, right? Here my domain set is fixed for some particular function. Every input should give some output, right?
Yes.
Something like this you should get. It should not be that I have fixed my domain set and for one particular input, the function does nothing. There's no output only, right?
Yes, sir.
Correct. So all elements in A should have a corresponding image in B, right? All
Yes.
elements in A should have a image in B, should have a image you are saying, but that is just the output, right?
Yes.
So that is one major restriction. That is the restriction that I said, that all values of inputs, it should give some answer. Okay, correct. What is another, can you think of another reasonable restriction on a good machine? What is another restriction that you would impose on a decent machine? Like we have talked about, you should give good inputs to it, the allowable inputs. You should expect an output if you give an input to the machine, right? What is something else from a practical standpoint? What would you call a working machine, proper machine? Think about it.
Um,
Any other restriction that you can think of?
Maybe the time.
No, time is fine. Time is not a major restriction, because there are different types of machines, right? Like for example, our body could be thought of as a function which takes in input and produces like growth, right?
Yes.
It takes 70 years to live and die, right? So uh, time is not a, there are different types of functions, right? So, like it could be totally different, right?
Yes.
So let's think of something else, some other restriction which makes something a good machine or a reliable machine, right? One restriction could be that, suppose I gave an input 2, right? And the answer
Yes.
came 5, okay? And then on 3 days later, I gave input 2, the answer should not come 1.
Okay, so it should have like a set. For every input, there should be a set output.
Correct. So it should not be like today I am giving one output, tomorrow I'll give some other output, right? For the same
Yes.
input,
Yeah.
right? That machine is completely useless. If it is it is like that, then you don't know which one to decide, right? What is the value when you give certain input, you will not even be able to know, right?
Yes.
Because it has multiple options, right? So so you should have a situation where every input should give only one particular output, right?
Yes.
Correct. It should not have this type of situation where one arrow from here is two arrows are going like this. This is wrong.
Each
Okay,
input should have like a set output.
correct. Each input should have a set output. It should not be multiple choice there. Okay, correct. No,
Yes, sir.
but this is okay. Okay, so for example, this can happen. Okay,
Yes, sir.
two different inputs could give the same output, but this cannot happen. This and this, right?
Yes, sir.
One input should not give multiple outputs. Two inputs could have the same answer. That's fine. So for example, y is equal to x square, right? Minus 2 and 2 will both give answer 4, right?
Yes, sir.
Correct. But you should not have like, for 2, you should get 4 or 6. You understand?
Yes, sir. Yes.
So basically the idea is that each element in set A has a unique image in set B, right?
Yes, I understood.
Okay. So oh no, I said the wrong thing. Each element in set A, I should say each output value in set B has a unique input, right? Each
Yes.
output value should have a unique input. It should not be that, because then minus 2 and 2 are not unique if they're giving 4, right?
Yes, yes.
Correct. So these are the two restrictions. So because of these two if these restrictions are satisfied, then you call it a function. Okay, function from A to B. So you'll write it like this: function from A to B, where A is the domain and B set is sometimes called the codomain. Okay, and let's say here there are these numbers. Let's think about the function, simple function y is equal to x square. Okay, and these numbers are minus 1, 1, 2, 3, 4, and so on, right? Here these are numbers minus 1, minus 2, 4, 9, 1, and so on. Okay,
Yes, sir.
Think of this as the set of all real numbers here, all real numbers here also. Okay. So since y is equal to x squared, any real number can be given as input to this, no? Because there is no problem with this function, no? It doesn't break down on zero or anything, right?
Yes, sir.
So the domain set for this, the domain is all real numbers. Real numbers is the domain, right?
Yes, sir.
Now the codomain set could have been this. B set could have been real numbers. B set could have been real numbers. However, notice one thing. Whenever you do a square of something, right, it turns out to be positive only, right?
Yes, sir.
Right. It will turn out to be positive. Only the positive numbers will have counterparts here, no? Correct.
Yes, sir.
So do you understand what I'm saying? You will not have any negative number here, will not have any input here, right? There's no
Yes, sir.
connection, right?
Yeah.
So that is actually fine. So that is fine because you could have a big B set out of which only a small fraction of values are being covered by some inputs like this. And some of them are left untouched, right?
Yes.
However, that is not fine for set A, okay? It should not be set A has 4-5 inputs which have outputs, but 2-3 inputs have no outputs, right? Correct? That was the first restriction, right?
Yes, sir.
So a function satisfies two constraints. All elements in set A should have some output. And the second constraint is every output in B is linked to only one element in A, right?
Yes, sir.
The set B is called codomain, and it could be a large set, whereas the set of actual outputs, of the function is called the range set, is called the range. So basically what I'm saying is that a range is the set of positive numbers here because it was y is equal to x square function, right? So only
Yes.
positive numbers will come in there, right? So range is set of actual outputs of the function. And okay, so we can also say now that
So
range,
positive and zero, right?
positive and zero. So range in this case is a subset of the codomain, right?
Yes, sir.
Range is always a subset of codomain. Sometimes it can be equal to codomain also. Like for example, suppose I had taken set B as set of zero and set of non-negative numbers, right? Then
Yes, sir.
obviously all of that element in here will have some root of that, right? Some input in set A, right?
Yes, sir.
Every element in set B in that case will have some input from set A, right? So that will be a situation where you have range is equal to codomain, right? Because set B
Yes.
itself was called the codomain, and now range is or allowable outputs are becoming codomain, right?
So range
So
is basically from the codomain, whatever outputs are used, basically.
yeah, and most of the times it is smaller than the codomain, but sometimes it could be that the whole of the set B is the range, right?
Yes, sir. Got it.
So that is a function, and that's all that you need to worry about right now. The thing, many times there are questions like this: suppose y is equal to x square minus 1 by x square minus 3x plus 2, right? Find the domain. Find the domain for this function. So that is fairly easy here. X square minus 1 is not a problem, but this part cannot become 0, right?
So you can factorize it and find the zeros.
So x cannot be 1 or 2. Other than 1 or 2, everything else is fine,
Yes, sir.
right? So that will be the domain. Uh, Obviously, there is a lot more to functions. There is operations on functions and stuff like that, composition of functions, more things that we'll learn later. But for now, this much information is enough for what is a function. It's a relation
Yes.
between input and output. The relation can be specified by a expression, and it has to satisfy certain conditions for it to be called a function, right? Those
Yes, sir.
conditions we have just now discussed. So now the next idea in calculus is limits. Okay, one nice example I want to give before we go on. So okay, so tell me whether this represents a function or not. Okay, wait, I'll do it on the next screen. So this is a situation. I'm making a table. I'm making a table of values. Okay.
Yes, sir.
So this is my x, this is my y. Okay. So x is 1, y is 3.1. X is 2, y is 3.14. X is 3, y is 3.141. X is 4, y is 3.1415. X is 5, 3.14159, and so on. You understand the pattern?
Yes, sir.
Correct. So now, is y is equal to f of x a function? That is the question. A proper function, basically.
No, sir, because like the digits of pi, right? So it's like randomized.
It's like randomized as in
As
pi
in,
is
like there's no
irrational.
set relation between.
Pi is irrational. You cannot predict the pattern and all. That's all fine, right? And it is going to go on till infinity, right?
Yes, sir.
So, so you're saying it's not a function, right?
Yeah, it doesn't form like a function.
But it does. That is the answer. It is a function. Why? Uh, why is this a function? Because think of the set A right here and think of the set B here. Okay. So set A is obviously 1, 2, 3, 4, 5 and all, na? Integers, right?
Yes, sir.
Go on till infinity, right? And set B is what? 3.1, 3.14, 3.141, 3.1415, right? 3.14159, right?
Yes, sir.
And will this also go on till infinity?
Yes,
Right?
sir.
Pi is irrational, it has infinite decimals, right, in its representation. Correct. Now, between these two sets, when can we say that it is a function? What are the two conditions that we spoke about? First condition was all the elements here, right, should have some connection here, right? Correct. You understand, no, what I'm saying? Hello? Can you hear me? Hello? 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 Can you hear me?
Yes, I can hear you.
There's some internet issue. Yeah. So what you're saying is for the function that we're talking about pi, right? That function. So all the elements of this set should have corresponding in outputs here, right?
Yes,
So is that the case in this case?
it is.
Because for no matter what number you go to, right, you will be able to find the decimal representation of pi and you'll say that that is the thing, right? If one
Yes.
was this here, then it is going to one decimal place. If two was there, it should go to two decimal place, right? And so on, right? There is a clear pattern, right?
Yes, sir.
Correct. So first rule is not is satisfied, right? First rule that
Yes, sir.
every element of set A has some output. What about the second rule? Is that rule satisfied? Second rule was saying what?
Yes, sir.
Second rule says
That
that there should not be two different outputs for one input, right?
each output should have like a unique input.
Excuse me. Yeah. So that rule is also satisfied, right? So what I
Yes.
want to tell you is that as long as these two rules are fulfilled, right? As long as these two rules are satisfied, it is a function. Are satisfied between two sets, between any two sets A and B, right?
Yes, sir.
Then you can say that there is a function between f from A to B. Now, why did I choose this example? Because if somebody asked you right now to write the description of that function, right? What is the relationship here? And it is impossible,
Yes.
right? So that is what I said when some functions could be mysterious, right? Like some functions you don't really know what is going on here. Like I cannot specify the relation other than saying it in English. Like mathematically, I
Yes.
cannot predict what the next term is going to be, right? Like I
Yeah.
have to find the value of pi by some other method and know the value of pi and then say, yeah, that is the output, right? But I don't know the process by which that next decimal is generated, right? Because
Yes, because there's no pattern.
there is no pattern there. Okay, so you cannot specify so this is a very special function where you cannot even specify what the relationship is, but you know that for sure there is a relationship. Okay, correct.
Yes, sir.
So this is still a function. Even if the box is mysterious to it, if it is a black box, even though that is the case here, it is still a function. Okay, because these two conditions are satisfied, 1 and 2. Every element has a counterpart and every one element has only one counterpart, right?
Yes, sir, got it.
Okay, so the second idea is limits. So this is a very interesting idea. Here you can think about this in terms of, do you understand anything about limits right now? What are limits?
Not really. Like,
Okay, okay.
is
So
it like
suppose,
what something approaches, like a value or
yeah,
something
it
approaches?
is that only. So suppose there is a dog, okay? This is a dog and this is a rabbit, okay? And the dog and rabbit are 40-meter apart. Fine.
Yes.
The dog is going at 10 meters per second and the rabbit is going at 5 meters per second, right? Will the rabbit catch,
Yes, sir.
will the dog catch the rabbit?
Yes, sir.
Sure.
Yeah.
In how much time? In how much time will the dog catch the rabbit?
Um,
That is not a very difficult question.
8 seconds, right?
Yeah. Relative distance is 40 and relative speed is 5, right? 8 seconds he will catch the rabbit, right?
Yes.
Correct. So, so I will give you a paradox here. There is a paradox here. It's called Zeno's paradox. So, so think about it. Uh, at the end of the first second, right? The dog has moved 10 meters, right? And the
Yes,
rabbit
sir.
has moved 5 meters, no?
Yes, sir.
Okay, so I started it badly. So what I will say is, how much time does the dog take to cover the 40-meter between them?
4 seconds.
4 seconds. In that much time, rabbit has gone ahead by 20 meters.
Yes, sir.
So rabbit is here, dog is here now, right?
Yes, sir.
After 4 seconds. Okay, then he comes here and realizes you have to go 20 meters more. So 2 more seconds, right? But
Yes,
in
sir.
that much time, rabbit has gone 10 more meters, right?
Yes, sir.
So dog is here, rabbit is here. I don't think he will ever catch two. Then he comes here, he's all, oh, he's 10 meters ahead. So 1 more second. In that much time, he has gone 5 meters, right?
Yes, sir.
So how will you ever catch? No matter where, no matter what happens, dog will always come to the previous location of the rabbit and rabbit will be slightly ahead, right? Consider them as point particles.
So, but the value approaches to zero as more time passes.
But it's still non-zero, right? Right?
Yes, sir.
So this is the paradox, right? This is the paradox that how does the dog catch the rabbit actually? So I want you to think about this paradox for a minute or two. How does the dog catch? Do you understand the problem?
Yes, sir.
We know that it will catch the rabbit, but it seems impossible. So this was Zeno's paradox that was proposed by a Greek philosopher called Zeno 2500 years ago. Okay, there was no calculus then.
Yes, sir.
2500 years ago, he said this, and everybody was puzzled because everybody was like, wait, what? Right? Because it
Yes.
seems like totally counterintuitive. Everyone knows that the dog will catch the rabbit, but nobody could show or prove to Zeno that yes, he will catch the rabbit. Like there's no nice argument that anybody could provide for almost 2000 years. Zeno's paradox was unresolved. Like after calculus was invented by Newton and others, then people understood why this is happening. Okay.
Yes, sir.
So because it was unsolved for 2000 years, why don't you take 2-3 minutes to think about this? I have to actually get on a call. I'll be back in 2-3
Yes.
minutes. Okay. Yeah. Hello. Are you there?
Yes, I'm there.
So, any ideas, any answers to this?
So I could just think of the fact that
Hmm.
for
Yes.
longer distances,
Hmm.
the difference, I mean, the distance between them reduces.
Distance between them reduces,
Like
right?
it becomes closer and closer to zero.
Correct. So what you can say is that the separation between them, if you think about the separation between them, right, that becomes
Yes, sir.
smaller and smaller, right? Correct.
Yes, sir.
So, or you can think of like how much time will it take to catch, right? So let's calculate the time taken to catch. Okay, so this next one will be half second, right?
Yes, sir.
This 5 meter, and the next one will be even smaller, 1/4, right?
Yes, sir.
Because he would go 2.5 meter in that time, right? So if you just think of the time taken to catch, it will come out to be 4 plus 2 plus 1 plus half plus 1/4 plus 1/8 and so on, right?
Yes, sir.
But Zeno's statement was that this will be infinite, right? Because
Yes, sir.
you will forever have to go a little bit, go a little bit, go a little bit, and so on, right? Even though the
Yes.
values are becoming smaller, the number of such times that you have to do this process will become infinite, right? Now, this was the problem, that the time to catch is becoming infinite. Okay. Time to catch is becoming infinite, right? Correct.
Yes, sir.
However, people realized that that was one of the key things that calculus tells us, is that sum of an infinite number of terms, number of positive terms, could still be finite.
It's finite.
Positive terms could still be finite, which nobody would have expected.
Yes,
Like,
sir.
like it looks like it's a positive term, no? So it should add up only, it should increase, right?
Yeah.
But the answer is that it will still add up to a fixed finite value, not infinite, even though you go to infinite terms here. Okay. And when you have done in 10th standard GP, right? You did GP, right? Geometric progression.
It was deleted, but
Oh, okay. Okay.
it's
But
like constant multiplication, right?
constant multiplication. So here you see the common ratio is half, right? Every time you're multiplying with half.
Yes, sir. Yeah.
So people figured out the sum of a GP. Okay. So A plus AR plus AR square plus AR cube. Okay. This one, if you sum to
Yes.
n terms, right? The sum of the GP formula is A 1 minus R power n by 1 minus R. And we will derive this formula later. Right now, just you can take it on a faith basis, that this sum of this
Yes, sir.
n terms is going to be this. Okay. Notice that it is correct, because if you take just two terms, right, n is equal to 2, what is this? Tell me. 1 minus r square by 1 minus r.
Yes, sir.
So 1 minus r square will cancel. So 1 minus r will come. Right? 1 plus r will come on top, right?
Yes, sir.
And see the first two terms. It is a into 1 plus r. No?
Yes.
Three terms also you can say 1 minus r cube by 1 minus r. So this is x cube minus y cube by x minus y, right? So x minus y factor can be removed, right? And it becomes
Yes,
1
sir.
x square plus xy plus y square. That is the factor remaining. So 1 plus r square, right?
Yes, sir.
Multiplied by a. So you get the first three terms, see? Correct?
Yes, sir.
So the formula is correct. This GP formula is correct. Now think of, now people discovered this idea of a limiting value. So limit as n tends to infinity of this s, right? So n tends to infinity means what? There are infinite terms in this GP now, right?
Yes, sir.
Infinite terms in this GP. Then what we have to basically find out is what does this s value tend to, right? So
Yes.
limit n tends to infinity a 1 minus r power n by 1 minus r, right? This is the question. Okay.
Yes, sir.
Now notice here that r is equal to half, right? And a is equal to 4, no? First term is 4, r
Yes,
is
sir.
equal to half, right? So let's put that here. Limit n tends to infinity. So a is 4, r is half. So 1 minus half to the power n by 1 minus half, right? Correct?
Yes, sir.
So this becomes limit n tends to infinity. This becomes 8 into 1 minus half to the power n, right? Correct?
Yes, sir.
So now notice that if n tends to infinity, this 1 by 2 power n, what do you think the value of that will be? N is tending to a very large number, right? What do you think the value
Yes,
of
sir.
this is going to be? This will be
Very
0,
small
no?
number.
This will
Yes,
tend
sir.
to 0, right? So the limit will
Yes, sir.
tend to 8. 1 minus 0, 8, right?
Yes, sir.
So the total time is not going to be infinite, but 8 seconds. Okay. Which is what you
Yes,
had
sir.
thought of intuitively also, right?
Yes, sir.
Correct. So the idea, the idea of limits was a key breakthrough in the 1600s, and Newton and Leibniz were working on calculus, because of which now you can do so many things. So basically, because of limits, the ability to calculate the limit of a sequence of numbers, right? You will be able to define derivatives. You will be able to define integrals. So all of it, all of calculus that you will see is based on the fundamental idea of limit of a function. Okay.
Yes, sir.
Because before that, we had wrong notions like sum of an infinite sequence of positive numbers will be infinite, right? But that is not the case always, which is what we saw. And that is why Zeno's paradox was troubling many people. Okay. But now we will define limit in terms of a function now. So limit of x tends to a of fx, right? What does this mean? So think about the function, some random function like this. And this is my x is equal to a. And this is the graph of fx, okay? So
Yes, sir.
if x tends to a, that means what? The x values are approaching a. But realize that you can approach a from two sides, right? You can approach a from
Yes.
the lower side and from the upper side, right? Correct. So
Yeah.
basically a minus 0.01. This side also you can approach, or you can approach from a plus 0.01 side, right?
Yes.
Correct. So this statement means x is becoming closer and closer to a. It doesn't have to be equal to a, but it is going to be really close. Okay. And what is he asking? What is the value of fx in that case? Right? What happens to fx when x becomes close to a? That is the meaning of this statement. Okay. So if you notice, let's say we are traveling on fx, we are a point on fx and we are moving on fx. So as x becomes close to a, our point is going here, right? This point, this side, right? Correct.
Yes, sir.
So our point is approaching this value of f of a, right? This is f of a, right? Correct.
Yes, sir.
And from this side also, we will be approaching this f of a only, right? Correct.
Yes, sir.
So if f of x approaches some value called L, some value called L from both left hand side and right hand side, both left hand side and right hand side, then we say that L is the limit. Then we say that limit of x tends to a, f of x is equal to L. You understand what this statement means?
Yes, I got it.
So both sides you have to approach the same value called L. And if you approach from both sides the same value, then we say that the limit at that point is L. Okay. So for example, things can go wrong like this. Things can go wrong if my function was like this. I'll just define a function. This is like this and this is like this. So this definition, the function is this: y is equal to x square if x is less than equal to 0, y is equal to 1 if x is greater than 0. This type of function is called a piecewise defined function. Why is it called a piecewise defined function? Because for one piece of the real number line, it is defined in this way. And for another piece of the real number line, it is defined in a different way, right?
Yes, sir.
So now think about it. Near x is equal to 0, right? Near x is equal to 0. Suppose you approach from the left side, right? So your values are tending towards what? 0.
0.
Right? And suppose you approach 0, the same number 0 you approach from the right side, then your values are tending towards what? 1. Right? Because you are always
Yes.
1. No, above x you are 1, right?
Yes.
Above 0 you are 1, right? So you are going to be on this point, on this function graph. No, from here you will be coming, right?
Yes, sir.
So your values will be tending to 1 here and will be tending to 0 here. So left hand limit is not equal to right hand limit, right? Because left hand
Yes.
limit is 0, right hand limit is 1. So we will say in this case limit at x tends to 0 f of x, we'll say does not exist. Does not exist because we don't know which one to pick, right? What will we
Yes,
say
sir.
the function tends to? We don't know. Left side it tends to 0, right side it tends to 1, right? So we'll say that limit of x tends to 0, fx does not exist in this particular case. Okay.
Yes, sir.
Okay. So for example, I'll give you a weird function. So weird function like this. X, if x is rational and 1 minus x if x is irrational. Now this function is very weird. Okay, so it is defined properly. Okay, it is properly defined. No, so if someone asks you what is f of 2, what will you say? What is the output?
2.
2. But if someone asks you what is f of root 3, what will you say?
1 minus root 3.
So no matter what question I ask you, you will be able to give me the answer, right?
Yes, sir.
That is not a problem here, right? But can you draw the graph of this function? I mean, just thinking about the graph will give you a headache.
Yes, sir.
Why? Because many points you will know, right? Like for example, 0, you will be 0, right? 1,
Yes, sir.
it will be 1, right? It will be like a,
Straight line graph for the right hand side.
but not really straight line. Not really straight line. You understand the problem? Between any two rational numbers, there are infinite irrationals,
Okay, yes, sir.
right? Like between 0 and the next point, what is the next point after 0? There are infinite irrationals, no?
Yes, sir.
So next point, you don't know where to put, right? It should be 1 minus x graph will also come somehow, right?
Yes.
So near x is equal to 1, the value should become 0, right? Near x is equal to 1. Near x is equal to 1, there will be an irrational which will be very close to that, right?
Yes.
So the value, there should be an alternative graph like this also, right? Which is the 1 minus x graph, right?
Yes.
Correct. This is 1 minus x graph. This is x graph. This alternative graph is put on the irrational points, right? And this graph is put on the rational points, right?
Yes.
You understand the problem? That
So it's like plotting such a graph possible?
no, it's not possible. Like because I don't know the next point where it will be, whether it will be on this one or whether it will be on this one, right? So
Yes.
suppose I take 0 and some tiny rational number 1 by 9. I can find an irrational between them. There will be actually infinite irrationals between them. Right? So between any two consecutive points, you don't know whether it will be here or whether it will be here, right?
Yes, sir.
Correct. So can you answer any question like, as x tends to 2, what is the limit of x? Limit of x tends to 2 f of x here. As x tends to 2, normally you would have said 2, right? But
Yes.
there is another graph which is bringing you down towards -1, no? Near 2.
Yes, sir.
You understand the problem? Left hand limit and right hand, you don't know for sure where you're tending to, right? So
Yeah,
limit
because of the number of irrationals.
a
Because there is
number
no
of
fixed.
irrational. Yeah. So limit x tends to 2 fx does not exist here, right? Because you cannot even decide the tendency on one left hand side. Forget about the right hand side, right?
Yes, sir.
Correct. However, there is one special point here where limit exists. That is this point. When x is equal to half. When x is near half, both the values are tending to same thing, no?
Yes.
You understand?
Yes, sir.
No matter how you come near half, both irrational and rational are giving x is equal to 1 minus x, right?
Yes, sir.
So at x is equal to half, there is a limit. Limit x tends to half, f of x is equal to half. And that is the only point on this function where there is a limit. Every other point, there is a problem. You understand?
Yes, sir.
So the limit idea is not a very obvious idea. Okay. So don't think of it as some trivial thing like, yeah, obviously I understand what it means, right? It is not so trivial. It is quite subtle in the sense that you have to decide how a function approaches a certain point, like before that and after that. What is the approach? Are they both approaching the same value? If yes, then that is the limit. If they are approaching some different values, then limit does not exist. And sometimes things can be very weird like this, right?
Yes, sir.
Okay, so that is limits. Now, once you know limits, so what you should do right now is read the chapter on limits from Thomas and Feeney. After this, read the
Yes.
chapter on limits from Thomas and Feeney, so you will understand. He explains very nicely. You understand what has to be done. Okay, so that is important to do. Once you understand limits, we'll try to understand the idea of a derivative. Okay, so
Yes, sir.
derivative was defined to capture the fact that sometimes you need to find the instantaneous rate of change of a function. Instantaneous rate of change of a function. Okay, so what do you mean by instantaneous rate of change of a function? So far,
Like the
let's
slope at a given point.
a slope at a given point. But why is that true? Why is the slope at a given point going to give me rate of change of a function? Just because someone told me is not a sufficient reason.
Because it's the distance like traveled. It's like whatever you call rise over run types.
No, no,
It's
it is
like how
not.
much y moves for every change in x.
No, no. So slope is just slope of this tangent line, right? Slope.
Yes.
Why is that rate of change?
Because it changes with every point.
But that doesn't, just because something changes with every point doesn't mean it's the rate of change of this particular function, right? Many things can change.
Like at
X.
any instant on that slope, you
Hmm.
can take any point and the tangent to that line will be the slope at that point.
Okay, that is just the definition you're saying. Tangent to that point will be the slope of that point. That is the meaning of tangent.
Yes.
Tangent to the point is the slope of the line. Basically, it will have there will be a line which will be drawn through that point, and slope of that line is called the slope of the tangent. That is what you're saying right now. But what
Yes.
I am asking is, how is that related to rate of change of the function? Rate of change of the function, how is that tangent slope going to be related to rate of change? You understand the point? It is not sufficient to say that, wait, tangent slope changes at every point, that's why it is the rate, right? Because I can
Yes.
find many things which change at every point. Like if I have y is equal to fx, x also changes at every point, right?
Yes.
X also I can say is slope, the rate of change of the function. No. How are you connecting basically rate of change of the function to slope of tangent at some point? Like I don't see any connection. If someone asked me rate of change of a function, I would not think about tangents. How did you suddenly start thinking about tangents here? You understand? Suppose you are going on a car,
Yes,
right?
I understood.
From Bangalore to Chennai, right? This is some whatever kilometers, 300 kilometers, right? And you took 5 hours, right? If
Yes, sir.
someone asked you average speed over your whole journey, you would immediately say 60 kilometer per hour, right?
Yes, sir.
Average speed. Great, 60 kilometer per hour. If I asked you what was your speed at 10 a.m. when you were in the middle of driving, then you don't know right now, right?
So what the speedometer says.
Huh, exactly. But actually, that is also incorrect. But we'll come to that. So what I'm asking you is instantaneous speed at a particular time, right? Correct.
Yes, sir.
What we are asking you is instantaneous speed at a particular point. So how did tangent lines come in this? Right? You understand the point?
Yes, I understood.
So okay, so right now you said what the speedometer says, right? So let's think about how the speedometer says what it says. Like, do you know how a speedometer will say what it says? Like, how is it
Like
showing
the
the
distance I think the distance it travels for like a very short time before the
uh-huh,
like before it calculates it and the
uh-huh.
time it takes to do that. So
So basically the idea is that the axle of the speedometer wheels, right, will be rotating, right?
yes, sir.
So what the speedometer does is calculates how many rotations happen, in a small time. Like, I'm just making it up right now. Let's say that time is, say, 0.1 second, right?
Yes, sir.
So what the speedometer will be doing is it will have a meter which will measure in every 0.1 second how many times the wheel has spun, right? So if you know the number of rotations of the wheel, then you know in one rotation of the wheel you will go forward by 2 pi r, right?
Yes, sir.
One circumference you will go ahead, right? So n into 2 pi r is distance divided by delta t is the time, right?
Yes,
This
sir.
time is the 0.1 seconds, right? But and this is what you are going to show on the speedometer, and every 0.1 seconds you will show it so fast that everyone will think that it is instantaneous, right?
Yes, sir.
But this actually, if you think about it, this is also an average speed over that 0.1 second, right?
You can't have like an exact instantaneous speed.
But you can, which is why you need calculus. You understand?
Yes, sir. Like practically you can.
Practically, till 10th standard and all, you can't, right? You can't here, because here also you're doing actually an average speed over a short duration of time, right? But
Yes.
basically the speedometer is not doing calculus, is what we're saying. Not doing calculus during the journey.
Yes, sir.
What the speedometer is doing is distance by time only, that you also knew how to do. It is just doing it on a small time interval, right?
Yeah.
So if I wanted to find the exact actual speed, right? So if my distance time graph is like this, right? So now think about what was the meaning of average speed, right? Average speed was, if this was my distance and this was my time, right? You would have taken some time t1 and some time t2, right? And you would have covered this much distance or displacement, right? So you would have joined
Yes.
this two, and this much is the extra distance or displacement you have covered, right? Earlier you were at here and later you were here, right? So
Yes, sir.
difference in distance is this much, right? And this is the difference in time, t2 minus t1. So
Yes.
if I had asked you average speed over the time interval, over the time t1 to t2, right? You would have said
Distance.
delta s by delta t, right?
Yes. Sir.
Correct. Great. You would have said delta s by delta t, which you knew already that this is what you're supposed to do, right?
Yes, sir.
Now notice that this is a right angle triangle and this is tan theta.
Yes, sir.
So it is like a slope of this line, right?
It's the
Slope of
slope of
this
the
line.
yes.
Slope of the chord. Slope of the chord connecting 2 points.
Yes, sir.
Great. So this is what I wanted you to say, that average speed is the slope of that chord connecting those 2 points on the curve, right? Now, if if you want instantaneous speed, then you have to do what the speedometer does, but do it better than the speedometer. Okay. So what you have to do is bring the point P and the point Q close and close to each other. Okay. So
Yes.
suppose my curve is like this and point P is here, and I bring point Q closer and closer, right? It comes here, right? Think about the chord here and you bring it further close, right? So if you take limit of Q tends to P delta S by delta T, right?
Yes,
Think
sir.
earlier it was very widely separated. So you're getting slope of a different looking chord line, right? But when the points become closer and closer, the chord starts looking like the tangent, no?
Yes, sir.
So slope of the chord, this is slope of the chord actually, but it will start behaving like slope of the tangent, very close to tangent line, correct?
For smaller and smaller, right?
When Q
Approximation.
really comes close to P, right?
Yes, sir.
The chord Q and P point will almost become like next to each other, right? One point only almost, right?
Yes, sir.
Then it will be slope of chord will be same as slope of tangent, right?
Yes, sir.
That is why you are saying that slope of tangent is the derivative, is the rate of change. You understand? Because ultimately you are calculating average speed here, no, average rate of change here, right?
Yes, sir.
And now you have made the time interval go to 0, right? So what is this statement going to mean? This statement really means that limit of delta t tends to 0, calculate this ratio. That is called ds by dt, or derivative of t, derivative of s with respect to t, or slope of the tangent at that point, or rate of change of the function at that point. You understand?
Yes, sir.
This value. So basically, again, you notice that without the limit idea, you cannot do this. Without the limit delta t tends to 0, it is still an average speed. Okay. So the
Yes, sir.
key idea that is added is the calculus idea that you can now take limit of delta t tends to 0 of this expression. And if it is some value, that value is the rate of change of the function at that point. Correct?
Yes, sir.
So now think about it. I will draw a graph here for a random function f of x. For a function f of x plus h, and this is f of x, because my this point was x and this point was x plus h. Okay.
Yes, sir.
So what is the slope of the chord right now? It will be this distance, which is f of x plus h minus f of x. And what is this distance? This is x is going from x plus h, right? So
Yes.
so slope of chord would have been right now f of x plus h minus f of x by x, right? No, by h, right?
Yes, sir. By H.
This is slope of chord. So what do I have to convert it? What do I have to do to convert it to a limit or instantaneous rate of change? Well, right now what I've calculated is average rate of change, right?
Yes, sir.
This is average rate of change of the function from when to when, from x to x plus h. From x to x plus h,
Yes, sir.
right? So if I have to do actual rate of change of the function at this point, I have to make my h closer to 0, right? So limit of
Yes, sir.
h goes to 0, f of x plus h minus f of x by h is equal to my instantaneous rate of change of the function at x. At x, right? So this can be sometimes written as dy by dx or f dash x. These are just symbols. Okay.
Yes.
So this is just a saying that derivative you have found. Derivative is the same thing as slope of the tangent at the point, or instantaneous rate of change of the function at that point, and things like that. Like these are just different names.
Yes.
Ultimately, dy by dx is the value of this limit. Okay. If y is equal to fx, dy by dx will be defined as limit of h tends to 0, f of x plus h minus f of x by h. Okay.
Yes, sir.
So all derivatives that you have learned how to calculate or you have seen are basically just limits. And that is why it is super important that you understand the limit idea really well. Limits and derivatives, these are chapter 1 and chapter 2 in the book that I'll send you, Thomas and Feeney. Okay. So
So I should read both or just the first one?
read both. Read both the chapters, chapter 1 and chapter 2. And there is a preliminaries chapter before chapter 0 also, which has some basic stuff that you probably already know. This is a
Yes.
preliminaries chapter. Okay. So just go through everything, chapter 0, chapter 1, and chapter 2. Okay. So,
Yes, sir.
so what we will continue in the next class is calculating derivatives of different functions. Okay. So there are many types of functions where you have learned some rules to take derivatives, right?
Yes, sir.
So Alan, they would have told you some table of derivatives that you have to remember, right?
So yeah, they gave some, but I didn't really like
Ah,
remember them.
but now they would have given right now when they're introducing, they would have given some rules like y is equal to this, then dy by dx is this, n x n minus
N
1.
power x and minus 1. Yes.
So they will not explain it or show it and all, but they will ask you to mug it up. So don't do that. So what we will do is once we understand this definition of the derivative, what we will do is we'll just derive all of those formulas that are essential. Okay. So chapter 0, 1, and 2, go through them. We'll continue from this point in the next class, and hopefully derivative formulas we'll discuss. And after that, we'll start discussing maybe integral calculus in the next class. Okay.
Yes, sir.
So, but make sure you read through this because otherwise you'll forget everything that we have discussed today. Okay.
Yes, sir.
Okay. That's all for now.
Also,
Hmm.
sir, how much like regular study do I need per day? About like you were talking about hours, right? So how many?
I mean, right now there is no school, right?
Yes, sir. But it'll start in like May, I think. June,
So
sorry.
on a school day, I would recommend 5 to 6 hours, which might seem a lot, but it is not. There will be very little time to do a lot in 5 to 6 hours. On a regular day, 8 to 9 hours at least.
Yes. So this is like self-study. So is this like homework or like revision?
This is like whatever time you have free, right? After whatever time you have free in the day, this much time you have to devote to physics, chemistry, maths for JEE. Like
Yes.
what you do there, school homework should not be counted here, right?
No, like the
Uh,
homework you said, like
Obviously, all of that will be coming in this only. Like you cannot
okay.
do apart from this 8 9 hours. I'm saying all of that work that is involved, homework plus whatever you have to do, revise, read a book, read a chapter, whatever I'm saying you have to do, right? All of
Yes,
this
sir.
has to be done in these hours. But it has to be like a regular thing. Like you cannot be like, oh, these next 2 days I will just chill for a bit, right?
So,
Uh,
so whatever work you give at the end of the class is basically what should be done, right?
yes, yes. That's
There's
all.
nothing additional I need to do, right?
Nothing additional I need to do. Like right now, it doesn't seem like it's a lot, but it will become this much work will also be enough, I think. So whatever I will give you the work, that will be enough. So, and you will get additional things to do from Alan also, no?
Yes.
So it's not like right now it might seem like less, but this much is also going to be quite hard to do. So when we go to slightly more advanced concepts, you will need this much time at least to do the work that I say. Okay. So that
Yes,
should
sir.
be your goal, consistently putting in this much effort. This is essential. This much is essential. Below this, it will become a problem. Okay.
Yes, sir.
Above this is all fine. Okay. So keep that in mind. This is for a holiday.
Yes, sir.
Okay. That's all then for now. I'll see
Yes.
you
Thank you,
tomorrow.
sir.
Bye.
Bye.